Hello everyone, welcome to the tutorial of Lab 4. So in Lab 4 there are two tasks. In task 1, you have to basically design a 7-second display driver kind of thing. What will you do? You will have like 4-bit binary input. Let me just go here. So we will use these 4 switches as a 4-bit binary input. Okay, so suppose this is B0, this is B1, this is B2, this is B3. So you will likely you have to input binary numbers. Suppose 0. Let me give an example. Suppose if you input 0, this is if you convert this to hexadecimal, it should be 0, right? The task is to input this kind of 3-bit binary input, and you will display the hex digit in the 7-second display. So as you can see in the BASYS3 board, there are 4 number of 7-second display. So suppose we want to use this 7-second display. This one. So here we will display the hex digit corresponding to its binary input. Okay. Suppose let me go give another example. So suppose if the binary input is 0010, so the hex value for this thing is 2. So for this input, the hex digit should be 2. I mean, the 7-segment display should display 2. Now, so this is the pin diagram. You can say this is the pin diagram of of a 7-segment display in BASYS3. So as I have already mentioned, that there are 4 7-segment displays, and you have to turn them on. I mean, if you want to turn on AN1, you need to activate this AN1. So let's take one 7-segment display as an example. So these are like LEDs, and these LEDs are named as like this: A, B, C, D, E, F, G. And you know that suppose, and for an example, if you want to display 0, you have to turn on all of these LEDs except G, right? Then it should display 0. And in this way, you have to display all the hex digits in task 1. Okay, so let's go to the code directly now. Here, as you can see, this is the entity. So this is the entity. Here we are actually, let me show you with a box. And this is the entity, and this entity has these inputs like B3, B2, B1, and B0. So these will be the inputs. I mean, this is to represent these B3, B2, B1, and B0. This is to represent the 4-bit binary input, and then you have out. So there will be FA, FB, and all the way up to FG. So what are these actually? So these will drive the LEDs of the 7-segment display. Okay, and then these are AN0, AN1, AN2, AN3. These pins, these are also output. AN, AN3, AN2, AN2, and this is AN1, and this is AN0. Okay, so these are output. So we have to control the 7-segment display pins using these F signals and these AN signals. Okay, now let me go back here. As I have mentioned that we will be selecting these LED, this 7-segment display. So this is denoted as we will represent these to activate. There are 4 7-segment displays. I have to activate one. So we will activate this one. So this is like AN1. So so you have to send 0 to activate. So this is some kind of reverse thing. 0 means activated and 1 means deactivated. Because you may know that this is the 7-segment display here are common anode type. So what does it mean by common anode? Let me show you that. Okay, so common anode means the thing is reversed. When there is 1, you have to that means those are deactivated, and if you insert 0, that means that 7-segment display is activated. Okay, so suppose if you want to turn AN1 on, then you have to put 0 to AN1 and put 1 to other AN signals. Let me just draw that. So this is AN1 and this is AN0. This is AN2 and this is AN3. So we want to activate just AN1 and keep other AN signals deactivated. So we have to insert 1 or high signal to this other 7-segment display. So these are like so we are activating the AN1 by inserting 0 to this AN1 signal. Okay, now let's move to the next part here. Here, as you can see, so let's move to the code again. So this is the entity. In the entity denotes the inputs and outputs, and then let's move to here. So as I have already mentioned that we were putting AN0 to 1 because we want to activate just AN1.
to activate, we are passing 0 and to A and 1, and we are keeping 1 in the other 7-segment displays so that they become deactivated. Okay, now what is this? Okay, so we have to generate FA, FB, FC, FD, FF, and FG signals based on these binary inputs, right? So in the theory class, you have seen, you have seen this, right? The 7-segment display theory class. Here, if you go to this lecture 11, so this should be lecture 11. Let me just make it big. So as you can see, these how these A, B, C, D, E, F, G signals work is working. This is described in the theory class. So as you know that this A, B, C, D, E, F, G, these are for the LEDs. Okay. So if you want to turn the LED on, then again, this is common anode. So if you want to turn the LED on, you have to put 0. Okay. So for this is W, X, Y, Z here. In the theory class, it is represented as the 4-bit binary numbers are represented as W, X, Y, Z. But here in this code, we are treating them as B3, B2, B1, and B0. I mean, B3 is basically W, and B2 is basically X, B1 is Y, and B0 is Z. Okay, so that's how you can read these 4-bit binary numbers. So depending on the 4-bit binary number, you have to generate this A, B, C, D, E, F, G. So these are like the F signals here. Here we are denoting A, this A as FA, and this B as FB, and so on. Okay. So you know how to, you should know, like you should have using the K-maps for each of these A, B, C, D, E, F, G signals. I mean, you have to draw a K-map for A, you have to draw a K-map for B, you have to draw a K-map for C, and so on, and you will get FA, FB, FC, FD signal. The expression for those F signals. I mean, so if A, using a K-map, you can just express FA as a function of these 4 binary inputs like B3, B2, B1, and B0. Okay. And similarly, you have to write the functions for FB, FC, FD, and so on. And you, for each and every of these F signals, you have to write this in the code. So as you can see here, FA. So after getting the Boolean expression from the K-map, I have written the expression of FA. Similarly, I have written the expression of FB. I have written the expression of FC. Okay, so in that way, you have to write all the K-map based functions for FA, FB, and FC right here. So all of this, right, from A to all the way up to FG, these functions are written. So these functions came from the K-map. Okay, so that is how you have to write the design source code for this task 1.
So here is the constraint file. So as you can see, we need to use these slider switches and the 7-segment display. Okay, so here, as you can see, this is the V17, and this is the one. So here we are assigning B0 variable, and in the next pin we are assigning B1 variable, and the next pin B2, and in the next pin B3. So we have just assigned this B0, B1, B2, B3 variables to these slider switches right here in the constant files. Okay, then let's go to the 7-segment display part. So before this 7-segment display, let me show you these first, maybe this portion first, because there are 4 7-segment displays, and we are assigning AN0 to this one, maybe, and A1 to this one, and AN2 to this one. I mean, in this sequence. So this is AN0, and this is all the way up to AN3, and this is AN1. This is AN2. So we have created this AN0, AN1, AN2, and 3 variables in our source code, and now we are like mapping those variables to these things. Okay, as I have already shown you that here in our case we inserted 1 in AN0, AN2, and AN3, and we put 0 to AN1. So that's why only this AN1 will be activated. Okay, now let's move to the inside this 7-segment display. So inside the 7-segment display, so there are LEDs like A, B, C, D, E, F, G, and just we are like asserting, we are inserting this FA, FB, FC. So we have created these variables, right? FA, FB, FC, FF, and FG, right? And etc. So we are just assigning these these variables right in these pins. I mean the LEDs. So we are assigning those variables in the LED pins serially. Okay, so this is the constant file. That's all. All other lines are commented out. So in the same way we have done in lab 3, we have to create a project, and inside that project you have to put this design file, I mean .vhd file, and we have to also put this constraint.xtc file, and then you have to run synthesis, then run implementation, then generate bit stream. I have shown these things in lab 3. You have to just go through with the process, and you have to upload this into the FPGA board, and then you have to test it out, right? So
now, after uploading the code to the FPGA and turning the FPGA on, initially it should look like this. I mean,
it should show 0. And let me, so these are the 4 switches. We are treating them as 4-bit binary input. Let me write something. So this switch is B0. I mean, the rightmost is is the B0. This is B1, and this is B2, and this is B3. Okay, so currently all these switches are in 0 position. So currently this is like 0 0 0 0, so 4 zeros. So what is the hex value for the 4 zeros? Let me write that. Okay, so suppose these are 0 0 0 0. So if you convert this 4-bit binary number to hex, it should be 0, right? So that's why it's showing 0 right here. And now let's move to the second 4-bit, the second 4-bit number, which is 0001. Okay, so if we put 1 right here, then this binary number should what is the hexadecimal version of this number? 0001. It should be 1, right? So the display should show 1 right here. So let me do that. So I am turning this B0 switch to 1 position. So as you can see, so the binary number is like 0 0 0 and 1. So what is the hex version of this? 1. That is being shown in the 7-segment display. Now let's move to the second, the third number, which is 0010, right? So if it's let me write right here 0010. So this binary number represents 2 in hex, right? So let me do that. So here currently these are 0000. So I am putting this second switch from the right to 1 position, and currently this is 0010. The hex version is 2, and that is being shown in the 7-segment display. In this way, you have to check all the combination all the way up to 1111. Okay, so this is 4-bit binary number, so you will get 16 combination. So the display should show 0 1 2 3 4 5 6 7 8 9. Then it should show A B C D E F and etc. The hex digits. Okay, so let me check the last combination, which is 1111. So I'm putting all this to 1. So as you can see, currently the binary values are 1111. 4 ones. So that should represent the F in the hex digit. That's why it is showing F. Okay.
And that is what task 1 is. And now let's move to task 2. So what you have to do in task 2 is, so here, as you can see, there are 5 push button switches in BASYS3. So we will use this push button switch. So suppose these, again, similar to task 1, we will use this 7-segment display. So initially, suppose this is at 0. So 0 is like this, okay? And then what we have to design, so you have to select one push button from here. So let me choose this center push button maybe. So what needs to happen here is, if you push this button, then it should increment the hex digit. Suppose it's initially 0, then you press this push button, then it should move to 1 from 0. Okay, increment by 1. So this should show these values, and then if you again push this button, it should show 2. So with each press, it should be incremented by 1. The display, the 7-segment display should be incremented by 1. So this is what you need to implement in the FPGA. So to do that, what we need to do. So at first, let me show you an issue with these push buttons. So these push buttons are like mechanical switches. So this is a human push. Human fingertip. If a human fingertip pushes this button, it should take like near in the second range or millisecond range. Uh, the time it needs to push the button, it should be in millisecond. 500 millisecond to 1 second, or in that range. And this kind of BASYS3 board, the clock of this BASYS3 board has a very high frequency, like 100 megahertz. So what is it? The clock of this BASYS3 is is nearly 100 megahertz. So 100 megahertz means the time period is like 10 nanoseconds. So what does it mean? It means that the circuit, the system will be updated with the frequency of 100 megahertz. At every 10 seconds, the system will be updated. So which is too fast. But as you can imagine, that human press on these push buttons are likely in the second range. Okay, and here the circuit is being updated 10 nanosecond at every 10 nanosecond. So we have to accomplish this push button mechanism. To use this push button input to our system, we need to slow down the clock first. Okay, because what happens is, let me show you the mechanical issue, because this push button is a mechanical switch, so there is some kind of issues with that. So what is the issue? So suppose when you do not press this switch, this push button generates 0. Okay, and whenever you push 1, it should generate 1. Now this is like an ideal transition. So when you push this button, it should go from 0 to 1. But this transition is not this kind of smooth. This is an ideal picture. So what is the real picture? The real picture is like this. So if it's at rest, it's 0. When you press the button, because it's a mechanical switch, it actually instead of going directly to 1, it actually bounces between 0 to 1, and then after a certain number of bounces, then it stabilizes at 1. So these are like bouncing. Okay, but what is the problem with this? Okay, but the problem is, like, this is for one single push, not multiple pushes. So if you push once, then how many zeros you are getting? I mean, in this is a rough picture. So you are getting like 1, 2, 3, and ultimately 4. So for a single push, you are getting 4 ones. And then what happens if the clock is too fast? What does this clock do? I mean, at every 10 seconds, it will take the update. I mean, the circuit change update. At every 10 nanoseconds, the circuit will be updated. So if the clock is too fast, then it will, I mean, it will consider each of these ones. Okay. So what happens is with this is a very illustrative figure, but in reality, it will not only these 4 times. I mean, the bouncing will be very much higher in number. So to illustrate, I have just drawn 3 bounces, but in reality, it can be hundreds of bounces right here in this time region. Okay, in this time range, there could be hundreds of, there could be thousands of bounces. So at your single push, it will read like 100 pushes. So the circuit will interpret your single push as thousands of these pushes, because if you interpret one as a push, then there will be thousands of this kind of push in a single real push. Okay, so we need to solve this issue. Okay, solving this issue is called debouncing, because this is bouncing, and we have to solve this issue using the debouncing technique. So what is the debouncing technique? So there are 2 stages right here. So we have, at first we have to slow down the clock. So what happens if we slow down the clock? Suppose if we slow down the clock, then the circuit will update less frequently. What does it mean? So instead of updating, so suppose this is the system clock. So here, what happens at each rising age? I mean, the clock, when the clock transits from 0 to 1, then the circuit updates. So here, as you can see, if we just as you can see, this in this time region, we are taking 2 updates. Okay. So as you can see, here in this time region, we are taking 2 updates. So if we try, I mean, this is for illustration. If we slow down the clock, I mean, suppose the clock is like this reluctant. Let me show with a different color. Suppose if we just relax the clock like this, instead of this, I mean, instead of this, if we do this, I mean, I'm slowing down the clock. Then what happens? So in this whole time range, it will just take 1 update. Okay. So if it just take 1 update, then here in this region, when the clock is 0, whatever happens here, it does not take the update. Okay. So that is the beauty of slowing the clock. So if you slow down the clock and you take only 1 update in this unstable, I mean, by doing this, you are actually skipping these unstable ranges. So whenever the circuit is stable, after a certain time period, then you are taking update. So that is the function of slowing down the clock. So for this task 2, we have to slow down the clock. Okay, let me show you. So this is a module which is called clock divide. This module will take the main clock from the BASYS3 and it will slow down the clock. Okay, so there is a time constant. There is a variable like TC or time constant. So here we have set that variable to 15. So this this code, I mean, you can use this code as a template to just divide this clock. Let me show you. So what does this clock divide clock function module do? So suppose this is, treat this as a like a black box. Okay, so what it does, it takes a clock input clock, and then it generates output clock. And what is the nature of this output clock? It will actually slow down the input clock. That's it. So how much slowdown it can provide? Let me show you. So there is a formula. Let me show you that formula. So here is the formula. As you can see, the output clock frequency would be the input clock here. 100 megahertz is the input clock in the numerator, and 2 TC1 to TC plus 1 to the power 4. So TC is the time constant. So there is a control variable. I mean, there is a variable which is TC. So by tuning this TC, you can tune. I mean, you can control the output clock frequency. Okay. So if you currently I have plugged in 15. So if you put 15 in the place of TC, then you should get like nearly 760 hertz or something like that. Maybe if exactly it should be like 763 hertz, but you can control it. You can change it and you can test this. So here the clock divide, what is it doing? This module is taking the input clock from the BASYS3 board, and then it is dividing the clock. I mean, it's slowing down the clock, and it gives us the slow down clock. And then there is another module. So you can use this as a template for your future work. So if you need to slow down the clock, you can use this module. Okay. So yeah, and next another module we will and the module will be required for this task to work. So what is this? This module is called dB pulse, which is debounce pulse. So let me go back here. So what it does, so dB pulse basically takes the slow, slowed down clock, slow clock, and then what it does, it actually generates a pulse. Okay, generates a pulse. What kind of pulse? It converts a physical pulse to a digital pulse. Let me just write that. So this, what does it mean by digital pulse? We will use this as a pulse. This is a filtered pulse signal. What kind of filtered pulse signal? Suppose if you there is a push button, as I have already mentioned. Suppose this is a push button. So if you push it, it takes that. It takes that, and then as I have mentioned, that it can a single push can generate multiple high signals. Okay, so we want a single pulse, single output for a single push, right? But as I have already mentioned, that the single push will actually generate thousands, maybe thousands of high signals. So this dB pulse module should take those 1,000 pulses, and it will use the slowdown clock, slow clock, and it will use the signal from the push button switch, and it will generate a clean single pulse. By single pulse means single push. So single physical push actually generates multiple high signals. As you can see, let me show you that. This is 0 and this is 1. 1 means high signals. So for a single push, we are getting multiple high signals. So what will it do? So it will convert multiple high signals into one clean pulse. This should generate the ideal scenario. When you push, it should generate a clean one. Okay, so it takes the push button input as the input to this module, and also it will take the slow clock, and then it generate a clean pulse. Okay, so you can use this as a template for your next work or project, maybe, because you can just treat this module as a black box, where in this module you can take the clock input, the slow clock input, and then your physical push button input, okay, as a key, and then you will get a clean from your mechanical push, you will get a clean 0 to 1 transition. So that is the function of this dB pulse in a nutshell, actually. So that is what you need to understand properly. What is its input and what is its output, and then you can use this module to do other works. Okay, so this is just a building block for this task 2. So where you can get a clean output pulse from a mechanical press in the push button switch. Okay, so so this dB pulse needs this clock divide because it needs a slow clock. So clock divide is actually taking the original clock from your BASYS3 and generates a slow clock, and dB pulse taking this slow clock and the mechanical push from the push button and generates a clean 0 to 1 transition. Okay, now let's move to another block, which our module, which we will use for the task2 main file. We have not reached to the main file of task2 yet. These are the required file to run that task2 main code. So this is the third portion here. This is a D flip-flop code. This is a code to implement a D flip-flop. So what does a D flip-flop look like? So this is an input signal for a D flip-flop, and there is a clock signal for a D flip-flop. Okay, and here and there is an output. So what is you will learn about D flip-flop in the theory classes, actually. So suppose this is a D input and this is the clock input and this is Q output. So in the positive edge of the clock, as I have mentioned, that the clock is like this, and it goes from 0 to 1 and then 0 again, then 1 again, and then whenever there is a positive edge, 0 to 1 transition, then what it does, it just transfers the whatever is in D, it transfers it to Q. Okay, so that is the function of a D flip-flop. So we will use this D flip-flop. So as you can see, what I have already told you, that is written here in language. As you can see, clock event is the transition, and clock 1, this represents the positive edge. When there is a change in the clock, it can be 0 to 1 and 1 to 0. Then clock event generates a high signal, and we are making sure that we are taking the positive edge. That's why we are also adding the condition of being clock equal to 1. Okay, so that's ensures that we are taking this edge, and as you can see, Q out is the output of this D flip-flop, and D in here is the D in, and this is Q out. So what it does, whenever there is an edge in the clock, it just transfers its input D in value to its output Q out. Okay, that is a D flip-flop, actually. Now for this task 2, we also will need the 7-segment driver that we designed in task 1. Okay, so we will just use this to just run the to properly run the 7-segment display of the FPGA. So I have just copied and pasted from task 1 the 7-segment display driver code, actually. Now let's move to the main top file. I mean, this top file will use all these 4 files. I mean, the clock divide, DB pulse, D flip flop, and 7-segment driver code that was implemented in task 1. Let me show you how this works. Yeah, let me just draw something. So here, as you can see, this is we are creating an entity. I mean, suppose this is a black box, and you have a clock input, which is the main clock from the FPGA board, and then you have button. Button is the push button. Let me, yeah, button is the push button, and then we have output like F A, F B. These are for like activating the LEDs of the 7-segment displays. Yeah, 7-segment display F A and up to F G. Okay, and we also have to select which 7-segment display we will use. So that's why we also need to generate the 0 or 1 high or low signal for this AN0, AN1, AN2, and AN3. And we already know that we will be using AN1. Okay, so that's why these are like active. If we want to activate AN1, we need to pass 0, and if we need to keep the 7-segment display deactivated, we have to pass 1. So we are deactivating AN3, AN2, AN0, and we are just activating AN1. Okay, now let's see what happens. So we have just created this entity. Now, what is the architecture here? As you can see, so here we are creating a variable or signal, which is slow clock. As you can imagine, this will come from the clock divide, of course, and then signal step. Step is like the output of the DB pulse, the clean pulse that I was talking about. I mean, for a single push, a single 0 to 1 signal. Okay, and that is step. I mean, we are naming it differently than in the DB pulse. So the output pulse, which is named as pulse here of this code, we will assign this as a variable called step. Okay, and then we have, okay, so this should be a 3-bit up counter. Okay, so what do we mean by up counter? So here, so what is the task? So the task was to increment the value. Okay, increment the value, and we need to, let me bring that. What is that? Yeah. Yeah, so this is, let me clear these things. So here the task was to push this or press this push button, and then it should the 7-segment display D8 should be increased. Okay, so to design this, I mean, we have to use the D flip flops. Let me go back. Okay, so we will use D flip flop, and let me also clarify that. So the 7-segment display should show from 0 to 7. Okay, but why 0 to 7? Because we will be using 3-bit binary numbers to update the 7-segment display. I mean, for 000 to all the way up to 111. Okay, 001, 010, 011, and dot dot dot. Okay, so this is a 3-bit binary number, and using the 3-bit binary number, you can go up to like 7, right? 0, 1, 2, 3, 4, 5, and all the way up to 7. Okay, so we have to deal with 3 bits. That's why we need to take 3 flip flops. Okay, so let's start with this thing. So this is a D flip flop, and D flip flop has a D input. We are naming this as D0. Okay, so here. Okay, and then this is a clock, and this is output Q. Okay, and let's name it as Q0. And this is the second flip flop. Let's name it T1. This is clock, and this is Q1. Okay, now this is T2. This is clock, and this is Q2. Okay, so we need to use these variables. That's why we are we are declaring some variables like Q2, Q1, Q0, D2, D1, D0, etc. Okay, now what is this block doing? It is actually calling this clock divide signal, and it's actually sending the clock signal here and making it slow. Okay, so as you can see, so this is actually calling this clock divide function and making a slow clock. Okay, now let's move to this. This is a DB pulse, and this block is actually calling the DB pulse. I have told you, I have already mentioned that we will use these 4 files. So first, this block is slowing down the clock, and this block, what is it doing? So this block is actually, so calling the DB pulse, and it generates a clear signal. So because this DB pulse block has the signal names like this: clock 1, key, and pulse. Okay, do you remember that is the pulse was the output, and the clock 1 is the input, clock key is the input. So we have to match those names. I mean, we have to map those names actually. So we're passing the slow clock to this pin of this dB pulse. We're passing the btn variable to the key pin of this dB pulse, and we're passing the generated pulse signal from this dB pulse. We're saving this in this state variable. Okay, so that's what we are doing. And then here, as you can see, we let me come back here later. At first, let's do this. Okay, so this is actually calling three flip-flops. The first flip-flop, which is FF0. Here, what are we doing? So we are passing D0. I mean, we're connecting D0 with the D in pin of the D flip-flop, because here in D flip-flop, this is named as D in. I mean, the input pin is named as D in clock, and the output pin is named as Q out. Here, we are just passing those names. So T0 for the first flip-flop, D0 is the D in, and as you can see, the step is the clock. I mean, Y step is the clock. The pulse, I mean, here as you can see, the push button signal, I mean, what does this dB pulse was doing? It was generating a clean pulse from a single press. So the single press is working as a clock for this T flip-flop. Okay, so what is it doing? So we have a mechanical press from here, and dB pulse is taking the mechanical pulse, a press, and then it is sending these as a clock input for the D flip-flop. So do you remember what does the D flip-flop do? It will, when there is a transition from 0 to 1 in the clock, then it passes the D to the Q. Okay, so by pushing, we are telling the D flip-flops to pass the input to the output. I mean, this is a kind of update. Okay, so input is going to the output. This is kind of update. So by pushing this mechanical switch, I mean, by pressing this push button, we are telling the flip-flops to update. By update, I mean send the inputs to the output. I mean, this push button dB pulse output will be connected like this. Okay, so what is it doing? It is telling all the flip-flops to send the input, D inputs, to the Q outputs. Okay, so now let me explain what should be in the Q2, Q1, and Q0, and what should be in the D2, D1, and D0. Okay, here this Q2, Q1, and Q0 will represent the 3-bit binary number that will control the 7-segment driver code. So let me go back here. So in 7-segment, the code we have written for task 1, what was it doing? It was taking a 3-bit binary number and converted it into the kind of hex digit display or something like that, right? So it takes 3-bit binary number. So to run the 7-segment display, we here, or maybe 4-bit binary number, whatever. So but here in the task 2, we will just use 3-bit binary number. So we will just keep the most significant bit to 0. That's how we can convert this 4-bit binary number code to a 3-bit binary number code, whatever. So what it does, so we have to insert a 3-bit binary number to the 7-segment display code. Okay, so this Q2, Q1, and Q0, this will generate the 3-bit binary number input to the 7-segment driver code. Okay, okay, so this Q2, Q1, and Q0 will generate the binary numbers like B0, B1. I mean, the Q0 will act as B0 to the 7-segment code. Q1 will act as the B1 of the 7-segment code. Q2, I mean, this Q2 will work as the B2 for the 7-segment code. Okay, and as I mentioned, the 7-segment code we have written for task 1 has 4 bits. There was another bit which was B3, but for task 2 we will use only 3 bit. So if you just plug in 0 to B3, then it will work actually. So because yeah, so this we are setting just B3 as 0, and we're dealing with the 3-bit binary number. Okay, now so we understand Q0, Q1, and Q2. And then what about D0, D2, and D1 and D2? So what will be these numbers? So as you can see that so Q1, Q2, and Q0, how these Q2, Q1, and Q0 are being generated from the flip-flops. So it is nothing but those D2, D1, and D0. Okay, so D2, D1, D0 is being passed to Q2, Q1, and Q0. Okay, when there is a button push. Let me clarify. When there is a button, I mean pressed button, then the D2, D1, and D0 will go to Q2, Q1, and Q0. Okay, I mean, okay, so here, if you think deeply, you can understand that Q2, Q1, Q0 is like the previous binary number before the push. So let me show you with an example. Maybe suppose your Q2, Q1, and Q0 is 0, 0, 1. Okay, initially it is suppose it is at a state where Q2, Q1, and Q0 is 0, 0, 1. Okay, these are being used as input in the 7-segment display, and corresponding hex digit, which is 1, is being shown like in the 7-segment display. Okay, now whenever I make a push, I mean, whenever I press, then whenever I make a press from this push button, then this Q2, Q1, Q0 should be updated. So by what value it is being updated? So as you can imagine that we have designed these three flip-flops in a way that when we press the button, then the D values should go to the Q2, Q1, and Q0. So what should we keep at D2, D1, and D0? If you think deeply, you should understand that we have to keep the next value in the D2, D1, and D0. What do I mean? Okay, so we have to design in a way. Let me clarify that. We have to design in a way that with a single push, I mean, with a press, the value. Suppose this is the Q values. Okay, let me write this Q. Okay, so if we design in a way that if we can keep D, if we can keep the next value of Q to the D, then what happens? Then if a press takes place in the push button, the D should go to the Q, right? So let me draw this this way. Okay, suppose let me just put it like this. So this is the Q value. So I'm just trying to use these three flip-flops in a single box. So this is the Q value. So Q is like 0, 0, 1. Okay, so this is the Q value. Okay. Now so here is D. So we do not know what to keep in D. Okay. The D flip-flop works in a way that if we press, then D will go to the Q. Okay. And we are also trying to do what? With our press, we want to see the next value. So the D should contain the next value, so that when we press the button, this D should go to the Q and we see the next value because Q is being displayed. Okay, so we have to keep 0, 1, 0 right here. When Q is 0, 0, 1, we have to put the next value in the D so that when we press the button, D goes to Q and we see the updated Q value in the 7-segment display. So that is how it works. It should work. Okay, so maybe in the theory class you will understand it more clearly, but this is the main functioning. Now, how will you get that? Okay, so how will you design in a way so that the D can contain the next value of Q? Okay, let's observe that. Now, let's generate the D values bit by bit. I mean, so let's start with D0. Let's start with D0. So D0 here. So these are the, I mean, the last bit is the D0. Okay. So how to determine the D0 so that it becomes the updated value of the Q0. Okay, let me just write this D2, D1, D0, and Q2, Q1, Q0. So this is the D, and this is suppose Q. So we are targeting in a way that D is the updated, I mean, the next value of the already existing Q. Okay, so design this D. Well, let's do it bit by bit. So let's start with D0. So for determining the D0 function, we have to write this. We have to express this D0 in terms of Q2, Q1, and Q0. Okay, so how to do that? So there are several ways to do that. So this is only an example. Here, let's decide on D0. So D0 should depend. How does this D0 depend on this Q2, Q1, and Q? Let's determine that. So D0 is dependent on Q. We are assuming that D0 is dependent on Q2, Q1, Q0. How is it dependent? So let's draw a K-map. This is, as I have already mentioned, but this is just an example. This is one example of doing this. Okay, so let me draw a three-variable K-map because Q2, Q1, Q0, there are three variables. So suppose this is Q2 and this is Q1 and Q0. Suppose this is Q1 and Q0. Okay, so this is 0, this is 1, this is 0, 0, this is 0, 1, this is 1, 1, and this is 1, 0. Okay. So how to determine D0? So D0 is the next value of Q0. Okay. Now, when the Q2, Q1, and Q0 is 0, 0, 0, I mean, whenever this is 0, 0, 0, then what is the next value of the least? Here, D0 is the least significant bit. Okay. So what is the least significant bit of the next value? So whenever Q values are 0, 0, 0, so this is the Q value. When this is the Q value, this should be the D value. Okay. Okay. And again, if it moves to the next segment, I mean, if this becomes Q, then it should be this should become D. Okay, so in this way, this should propagate. Let me go step by step. So when Q, what does this box? I mean, this box. What does this box represent? The Q values are 0, 0, 0. So whenever the Q value is 0, 0, 0, the D or the D should be, the next value should be 0, 0, 1. And and here 0 is the 1 is the what 1 is the D0 value. So here it should be 1. Okay, the output should be 1. So let me write D1 as well. Let me draw the K map of D1 as well. I'm not drawing the Q. Similarly, here there should be Q2 and Q1 and Q2, etc. Q0. Let me draw this for. Let me draw this for the D2 variable as well. Okay. Similarly, this is Q2 and this is Q1, Q0. So whenever the Q is 0, 0, 0, I mean in these boxes, the D should be the next value of Q, which is 0, 0, 1. So here that should be 1, and D1 should be 1, and D1 should be 0, because here as you can see this is 0. Sorry, this is 0. Okay, and D2, this is D2. The most significant bit is the D2. That should be 0. Okay, now I have updated for this. Now let me move to the next box, which is here. So here Q2 is 0, so and Q1, Q0 is 0, 1. So 0, 0, 1. So we're looking for 0, 0, 1. So this is the Q value. If this is the Q value, then the D value would be the next one. Okay. So here, as you can see, D value is like D0 is 0. That's why I will write 0 here. And the D1 is the middle one, which is 1 here. And then the most significant bit is the 0. Okay. And now let's move to the next box here. In this box, this Q2 is 0 and Q1, Q0 is 1. So 0, 1, 1. So here is this. Well, let me. Okay. Now we are trying to fill up these boxes where Q2 is 0 and Q1, Q0 is 1, 1. So 0, 1, 1. So this is the Q. This is the Q value. And if this is the Q value, then this should be the D value. Okay. So D value is like D0 is 0, D1 is 0, and D2 is 1. Okay. So I think let me go here when the Q2 is 0 and Q1 and Q0 is 1, 0. So 0, 1, 0. So looking for this. Let me erase this. Okay. So we are looking for this box now, where Q2 is 0 and Q1 and Q0 is 1, 0. So 0, 1, 0. This is 0, 1, 0. If this is Q, this should be D. So D0 is 1, and D1 is also 1, and D2 is 0. Okay. So in this way, you have to fill in all these boxes of this schema, and then you will get an expression. I mean, if you do the grouping or looping, etc., then you will get the expression of D0 in terms of so D0, you will get an expression of D0 in terms of Q1, sorry, Q2 first, Q2, Q1, and Q0. You will get the expression for D1 as well in terms of Q2, Q1, and Q0. Similarly, for D3 as well, you will get a Boolean expression with respect to Q2, Q1, Q0. Okay. So if you do that K-map thing, you should get something like this. I'm not doing the whole K-map solving. You have done a lot of K-maps in theory classes. Use that knowledge. So here you should get something like this. The D0 expression should be Q0 bar, and the D1 expression should be Q1 XOR Q0, and the D3 expression should be something like that: Q2 XOR Q1 and Q0, something like that. But this is not a unique solution. Maybe you may get different things, but this is one solution. Okay. So if you implement these, I mean, if you have to update D0, D0, D1, D2 like this. So that's what I have done right here. So as you can see, I'm assigning this not Q0. I mean the complement of Q0 by not. It means the complement of Q0 to D0, and D1 is Q1 XOR Q0, and D2 is Q2 XOR Q1 and Q0. But if you get different kind of expression, you test those. I mean, you can test those expressions. But this works. Okay. And then yeah, so I have already discussed about these, because these are like just declaring those flip-flops. Okay, the three flip-flops. Okay, so for these three flip-flops, we have written the expression for the D values, and yeah, so D values are ultimately going to the Q values. Okay, so initially there will be a Q value of 0, 0, 0. Then the D values is actually going to Q. So we don't have to write anything about Q. Okay, so we have just written the expressions for D values. We have not written any expression for Q because Q is basically the D values. That's why this D is being passed to the Q values just with key press. The Q values are being updated with the D values. Okay. And similarly, when you are ready with all these design files, then you have to add the constraint file. This constraint file will also be provided to you. Okay. Let me also talk about this constraint files here. As you can see, I have activated the lines that deals with the clock. I mean, this will activate the main clock of the BASYS3, which is the first clock. I mean, this will be used as an input to this clock divide module, and it will just convert it to a slow clock. But we have to activate the clock. I mean, the clock of the BASYS3 board. So I have just uncommented this line so that it becomes activated. Now let's move to this. These are just like task 1. This LED 7-segment display pins are activated here. And another thing is here the push button. So here is the push button. I have activated the push button line here, and you have to make sure that the variable name was btn, so that's why I have written btn right here. So the btn variable is connected to this push button. Okay, so that's it. So this is the constraint file. This will be provided to you. Okay, so that's how the after you have taken this design source files, and let me go back. Yeah, so you have to keep all these files in the project directory, and then in the similar fashion shown in lab 3, you have to just run synthesis, then run implementation, then generate bit stream, and then upload that bit stream and the file to the FPGA, I mean BASYS3 FPGA. So this is all about lab 4.
So this is how the FPGA BASYS3 board should operate. Currently, when you turn on the FPGA and you upload the code to the FPGA, it should show like this. So as you can see, this LED, sorry, the 7-segment display is showing 0 initially. Then there is a push button switch right here. So I have to press it. So if I press it, it should go to 1, right? So let's press this thing. As you can see, if I press it, it goes to 1, and then press again, it's going to 2, and then press it again, it's going to 3. I mean, it's being incremented, right? So in this way, you can just keep pushing, and it should go up to 7, and then it should come back to 0, because we are using 3-bit binary bits to drive this 7-segment display. So that's how task 2 works. Thank you for listening to this tutorial.